analog instruments as discussed in the previous lecture. Now we are going to see about the layout design for CMOS inverter in Cadence Virtuoso. The window that has been projected in the screen is Virtuoso window. This is Virtuoso window. This is library manager. So for our channel purpose, I am going to create new file, and so the new library is going to be YT. We are making in GPDK 45 nanometer, so I am keeping some 45, and I am attaching the technology library. So now we can see this, and to check the properties of that, you can right click and check this properties of the file. So the technology library is correctly attached. So now we can some new file that is called cell view, and we can name it as CMOS inverter, and always try to take schematic Excel so that you will get some more options. So yes, now we want to design the schematic for the CMOS inverter, and in CMOS inverter you can choose the elements like in the process being displayed. You can choose the NMOS. This will be the standard parameters. You have to select the symbol, unless you will not get the symbol NMOS. Sorry, you need not to have this. The bind key for instance is I, and the caps lock should be off. You can browse the device. PMOS 1 volt represents the threshold of voltage for the transistor. You can click F for fitting the device in the screen, and also for suppose if we zoom out, you want to see only this. If you have a mouse, click right click, select the area, then it will be zoomed for that particular area. If you click on this one, it will be fit to zoom as similar to F bind key. Now we can draw wires with bind key W with caps lock off. You have to connect some pins for this inverter. Those includes bind key for creating pin is P. You have to keep it as input. You can put A. You can keep it here. Similarly, another for VSS and VDD, we can click input output IO pin. You can select this. You have to make sure this is connected properly. And one output pin we have to keep, that is, let us say the output is INV, or it would be better if we choose A bar. You can select the device, click M to move the part of the schematic, and you can move the part, and again you can draw the wire. Yeah, you can check and save here. Now we have two warnings. That is because of we neglected the connection of bulk. Most of the people connect bulk with the source, but that is wrong. Always remember, PMOS bulk should be connected to the VSS. We will discuss about that, but for now, for inverter you can short, because as source will be connected to the VDD and VSS, you can connect, but you have to make some difference like this. Since it is source is connected to VDD, I just shorted, or else you can just, okay, that's fine. But remember, bulk should be given to PMOS bulk should be given to VSS, NMOS bulk should be given to VDD. I think I just placed wrong instances. This should be VSS and this should be VDD. So now it's fine, it looks fine. VDD, VSS, bulk is connected, and you have to check and save. Now you have no errors and warnings. The shortcut bind key for check and save is Shift plus X. Now you can launch the layout Excel. Try to use only Excel or GXL. Create new. Now while doing the layout for standard cells, there are certain rules to follow. You have to create some PR boundary, but before that we have to bring the objects. Now below you can see generate all from source. This option is generate instances, or all the instances from the source schematic, or else we have another option called generate selected from source. Now if I selected it, try to make minimum separation as 0, so that you will get instance like this. The device, change the values of the PR boundary. The bind key I used is Q, selecting the PR boundary. Either you can also create a PR boundary using via create PR boundary, like that also you can create. But now I just created like this. You can choose this metal pins. To choose multiple objects, you can click on the first object, press on shift and choose the next objects, so that you can select all of them at a time and follow these instructions. Make them as pins. The next thing you have to do is that you have to align this transistors to the PR boundary. Yeah. Now you have to create bulks. N tab, that is NL for PMOS, P tab for NMOS. Another thing, you can just create some 2.2 thing. Very nice. 0.22 if I say, you can just keep this constant. So like you have to maintain some standard distance. Since it is aligned with the center, I'm just taking from this, or else um, here you can just move it. Similarly, you can take this. Here I think this is not aligned properly. Yeah, this is not aligned properly, so I align it. Yeah, now the center is aligned, so you can use this. Yeah, now it's fine. For extension, you have to use some 0.2 micrometers. Yeah, that's fine. You have to create some 0.2 micrometers of extension, that is required for DRC and fabrication purpose. You cannot just leave it like that. You have to follow the same rules. Align properly. To check these connections, you can select here, it will be highlighted. It will be highlighted. Similarly for those also. Yeah, now we can make those connections. So I am using this like from the bottom I am connecting, just because if we make some uh, changes in transistor, like if we move it up or down, it will be adjusted, and also we can adjust later also, but it is more chosen way. And another thing, here we can see the layers that we can choose. I've been using, we can choose that, and if we click on here, only those layers will be visible. And you can see those measurements. For those bind key is K, you can choose K and you can measure. And to delete all those measurements, you can use shift K, so that all of the measurements will be removed. And to undo your action, you have to use the bind key U, so that your actions will be undone. Now you can see this metal, you can see some discontinuity here, so we can just create some new metal for a quality layout. Yeah, now you can see, you can also see the layer by layer, pin by pin. You can see this, these pins are some misaligned, like the dimensions are not in matching with the metal over it. So you can choose those two metals and change its dimensions. So I just chosen those two metals. When you are making changes for multiple objects, press on common changes. So the 1 2 is the length of this tab 1, so that's why I use it the same length, and make it center. Similarly the bottom pin also can just move it to the center. Yeah, you can see we have to make this connection also. Yeah, it's fine. Now I think we've given all those connections, and the main thing is, if we see this N well, we have to make sure that the transistor and the bulk connection, that is source and bulk connection, we've seen this in transistor, bulk is same as transistor, they both are present in one N well. So we have to create one big N well. Before that, we can see here, we have to maintain some spacing, that is 0.06 from implant to the N well. Similarly this side also, can mark this and create some new N well. Yeah, choose the layer that needs to be drawn. See, now we are facing one issue, like I'm typing R, but the pointer is not in the same. In this conditions, click Shift plus E, we see gravity is on. In this case, we cannot point the objects as we needed. And also make sure this abort server is off. Now we can make the connections. See, now you are getting similarly. Yeah. Now we can see all the layers, right? Here we have to create wire. Try to maintain some spacing between them. Should have 0.06 spacing, and yeah, there is some DRC constraint. The minimum area of the metal should be 0.2. So what, we are just creating some new metal with higher area. So we can escape the DRC, check and save, run the DRC, check the technology library, 45 DRC, should have 45 nanometer technology. Here, run the DRC, save it. So we got some area issue here. Minimum contact active area to the gate. So this issue can be neglected, like when I run a DRC, if we can just remove this DFM check and run that, that can be clear. No DRCs. Yes. So that error is like the minimum spacing between these two. We can neglect, since the components of the transistor cannot be changed, so we can neglect that kind of errors, but make sure as much as possible to not have those errors instead of deleting the DFM file. Yes. So we can run LVS. So we got cleared for the LVS. Yes. Schematic and layout match. So I said earlierly, we have two major tasks, that is DRC clearing and LVS clearing. As of a layout engineer's end, we are supposed to make sure that we have no LVS issue and DRC issue. So for this inverter, we cleared those all, and to remove all those measurements, bind key shift K, I removed all those measurements. And here, when so we have to make like some connections, like we have NAND plus inverter is equal to AND. So when we are making AND connection, we have to connect this input with some other connection. Then we will not have this area concern. So in that case, what you must to do is that copy this layout to some another file and remove this metal and merge this metal pin with this contact, so that we can make a direct contact from this output of NAND to this or any kind of instance. Yes, thank you.